Let's just review some of our intermolecular forces before we get started to some new material here. Also another announcement, there's no lab today. Okay, the first lab on intermolecular forces starts next Tuesday. All right. So before we begin with kind of a new topic here, let's just review here what we went through last week, which was our first week of the semester. We talked about IMF. So I want to just give a listing, or maybe you guys can give a listing of some of the IMF's intermolecular forces that we have learned so far. So can anyone give me one? Okay, how about the strongest one? Ionic is the strongest, okay. And what do you think is the next strongest? They're both polar, so both of these are polar, but out of the polar, one is a little bit stronger than the other. Okay, actually both are dipole, or polar. This kind of means the same thing depending on whatever parlance you're in. They talk about whatever chemistry language. Yes, it's hydrogen bonding. Okay, and then after hydrogen bonding, what's the next strongest one? Dipole. Yeah, kind of this. Okay, so these two are essentially the same category, but hydrogen bonding takes the cake as being stronger. And then what's the weakest intermolecular force that we talked about here? Dispersion. Okay, very good. Right, so if we're going to label the strength of these, which is the strongest? And the ionic will be the strongest. Which would be the weakest? Okay, and then which would be the next strongest? Probably this, I guess, next strongest. And then this would be, I don't know, polar, dipole would be, I think, kind of strong. Now my labels are getting all askew here, but definitely you guys are correct. Ionic is the strongest, and then hydrogen bonding is the next strongest. What do we look for when we want to find something that could potentially, a molecule can potentially have hydrogen bonding? What three things are you looking for? Yes, okay. OH, NH, and then F. If you take biochem, this is a lot. Hydrogen bonding is a big deal in our cells, in the molecules in our body. There's also a fluorine that can also hydrogen bond. So those are essentially the three things that you're looking for. That doesn't mean if you see a fluorine, it automatically hydrogen bonds. You need a hydrogen. That's electropositive, and then you need the fluorine or the NH or the OH that's electronegative. So as an example of what I just previously said, even though F2 has fluorine, it cannot hydrogen bond because it is what type of molecule? Polar or nonpolar? Nonpolar, okay? So just because you see fluorine, you shouldn't just say, hydrogen bonding. This is fluorine, diatomic fluorine, but it cannot hydrogen bond because it's nonpolar. Okay, the dipoles cancel out. The poles cancel each other out. Speaking of dispersion, what type of molecules will display dispersion on an exam or on your MCAT or whatever big exam you're taking for your future? What type of molecules will display dispersion? What type of molecules? Nonpolar, okay. Okay, what functional group has nonpolar? Alkanes, very good. Okay. So we'll find this out in our lab next week, that alkanes have dispersion as their main intermolecular force when you'll work with these alkanes next Tuesday or Monday. And let's just do one more thing here, boiling point. Which do you think would have the highest boiling point? ionic will have the highest boiling point. Okay, which would have the lowest boiling point? Dispersion. Okay, and then here would be, I don't know how to rank this, but the hydrogen bonding would have a high boiling point, but not as high as ionic. And then this would have a high boiling point, but not as high as hydrogen bonding. A little high, I'll say. Alright, so that's what we want to get to in our exam that's coming up whenever. Just ranking boiling points based on the intermolecular forces. Here, again, hydrogen bonding. This is something I'd like for you to know, the OH, NH, or F. Okay? There's a functional group that has a lot of OHs in them. Do you remember what that functional group is called? Okay. You don't have to memorize it, but it would be good to know the functional group that's OH. Alcohol. Did you have some last night? No. Alcohol. That's just a joke. Right? Okay, alcohol. Okay. Hopefully it's not methanol. Methanol is called wood alcohol, and some of it. Do you know this story? Ethanol is what we have that they sell in a liquor store, but some cheap places, they want to cut costs, so they'll put methanol in there, and that actually leads to blindness. So, but anyways.
Is it charming sarcastically?
Charming, yeah.
Oh, charming, that's nice to have.
Yeah. So methanol, ethanol, propanol, butanol, so on and so forth. Yeah. Methane, ethane, propane. Okay. So you can have this for the exam. If you don't have a copy, you can get it to me after class, or I'll print it out. It's also on Canvas, by the way. You can. All right, let's go over some new material here as we try to get through Chapter 11. This is something that's a good short answer on the test. So short answer, just know these three properties of liquids. Okay, all liquids have them. Okay, so if it's a liquid, then it's going to have these three, or actually four properties. That includes not just water. Okay, that includes the liquids that you'll work on in the lab next week. That includes blood, biological, urine, biological. It includes whatever, rainwater. Okay, all, as long as it's that state, okay, that physical state known as liquid, it's going to have these three properties. The first one I'd like for you to know, again, short answer, surface tension. Okay, surface tension. So all liquids have surface tension. So what is surface tension? Okay, let's say you have a air-liquid interface. Air here and liquid here. Remember, all liquids have this. Okay, it doesn't have to be water, any liquid. Okay, right on the surface of the air-liquid interface, or maybe I'll say gas-liquid interface. Right on the surface of these interfaces, right on the surface, the area that touches it, the interface, okay, has a demarcation. Okay, the surface, right on the surface that touches the gas phase, and then at the bottom is the bulk liquid phase. Okay? That interface has slightly stronger IMF. Okay, slightly stronger IMF. Okay, so if it was hydrogen bonding, it will be slightly stronger hydrogen bonding. If it's dispersion, which is already very weak, it will have slightly stronger dispersion. Okay, just right on the surface that touches the gas phase. Okay, this is the bulk liquid here. That's not in contact with the gas phase. Okay, so that is slightly stronger intermolecular force to break it. It's a force. We call that surface tension. Okay? So on the exam, just know surface tension is what all liquids have. Some liquids have higher surface tension than others, okay? But we just need to know surface tension is a property, universal property of liquids. Okay? Whatever they may be, whatever liquid it could be. Right? So, and that surface tension is just to break it. That force to break it or disrupt it is because at that interface you have slightly stronger IMF there. Right? To break it, to stretch it, to compress it, that is surface tension. So I did this is a long time ago now. This is, 15, 16 years ago. I did my PhD thesis on the surface tension in the lung. So the alveoli in the lung, they have to overcome surface tension. And the way it overcomes surface tension is that the body produces lung surfactant. You can imagine 300 million tiny balloons. Those are called alveoli. And you can't, inflating and deflating a balloon that you do for a birthday party or whatever is fine. But these are so small. They're like micrometers in diameter. To inflate and deflate these tiny balloons is very difficult. So the body produces a substance that minimizes this surface tension, in the alveoli. This is called lung surfactant. And premature infants don't have this. They lack that. So anyways, the point being that right on the interface between the air and the liquid, or the gas and the liquid, those two phases on the surface, you have slightly stronger IMFs. To disrupt that, to stretch it, to compress it, that force is surface tension. For the exam, all you need to know, surface tension, property of liquid. Just connect those two dots.
So surface tension, property of liquid, that's all we're going to do about on the exam.
Yeah. Just want you to know that. All right, surface tension is one property of liquids. What's another property of liquid? Okay, the other property of the liquid is adhesion and cohesion. All right. Okay, so cohesion is the intermolecular attraction between like molecules. Between like molecules. Between like. So that is cohesion here. Have you guys heard of this term called meniscus? How many of you have heard the term meniscus? You have, Jacob? Right. Okay. So just the attraction between the liquid molecules make, when you're measuring the volume of something, you're measuring, it kind of goes like this. Okay, so you read the volume from the meniscus, that's all. Okay, because the cohesion makes it, the volume kind of tamper down. It's hard for me to explain, but anyways, it's something like this. Okay. So cohesion is what all liquids have. And then the final one is adhesion. Okay, the attraction between unlike molecules. On the exam, you just need to know adhesion and cohesion. Associate that with all types of liquids. And this is the attraction between unlike molecules. Have you heard of the term capillary action? How many of you have heard the term capillary action? Okay, how many of you have ever had your blood drawn for glucose using a glucose strip? You have done that, Eric? Okay, so what happens when you prick your blood and then you put it in the strip? What happens to the blood? It sucks up. Okay, it sucks up, and then you take that strip, you put it into the glucose meter. You can buy these glucose meters at CVS or Walmart pharmacy. Okay, so people with diabetes, I have diabetes that runs in the family, so I did this for my brother. You prick it, you know this, right? You prick it, and then you take it on the strip, and then the blood just goes right on the strip. Okay, do you guys know what I'm talking about? Okay, those of you that do blood checks for diabetes. anyways, that sucking up, okay, that ability for the blood to just go in, or that water to just go up, is adhesion, and that is another property of liquids. Okay, so you can have this with water, you can have this with blood, you can have this with any type of liquid, just varying degrees of cohesion and adhesion. Right, so this is the second, or you can say second and third properties that all liquids have. Right, the final property that liquids have is viscosity. Okay, so what do you guys think of when you think of viscosity? Okay, so viscosity means resistance to flow. Okay, this is the fourth and final property that all liquids have, some sort of resistance to flow. So what does that mean? Okay, when you pour something, it can either pour very smoothly, or it can pour like molasses, okay, like syrup. Okay, how does syrup go? Okay, it droops down. Okay, how does water flow? Okay, that's a nice word to put it. It flows smoothly. So all types of liquids have varying degrees of viscosity. Right. So have you guys heard of antifreeze?
I've heard that don't let your pets eat it.
The pets eat it? Okay, don't make sure that pets don't drink antifreeze. It's used in some coolants. So antifreeze, the main ingredient is some form of glycerol. So let me draw the structure of glycerol. Okay, this is glycerol. So one thing I want you guys to know about antifreeze or syrup or molasses you may have heard of is that they're very viscous. Okay, you may not have heard of antifreeze, or you may not have heard of the main constituent glycerol, polyethylene glycol. Okay, all of these are very viscous, so they flow like syrup, very droopy. So one of the things, especially with regards to glycerol and a lot of substances that are very viscous, is that they tend to have a lot of OH groups. Okay, OH groups. So what do we know about OH groups and the intermolecular forces that are involved with them? Okay, hydrogen bonding. Okay, so one of the things that very viscous substances have is that they have extensive hydrogen bonding through the OH. It's not just one moiety of OH, but several moieties, several OH groups within the molecule, and that imparts upon it viscosity. So on an exam, if you're given a list of molecules, which one do you think would be the most viscous? Okay, without ever looking at them. Anything with multiple OHs. Glycerol is an example, okay? But yes, anything with multiple OH groups, because of that ability to really hydrogen bond. I mean, this is hydrogen bonding, on a next level, because they form networks. Those tend to be very viscous. So the antifreeze that you buy from the auto store, the glycerol that's found in Walmart or even in our lab, okay, they're very viscous. And a lot of OH groups, those molecules that have a lot of hydroxyl groups, okay, this one has 3 hydroxyl groups, tend to be very viscous. So associate viscosity with OH groups and the hydrogen bonding network.
So that's viscosity. If you have like a lot of H bonding networks, it's going to be very viscous, correct?
Yeah, a lot of H bonding, okay. Lots of, okay, so a lot of OH groups, okay, and usually that lots of H bonding is because of lots of OH groups. Okay, this has multiple OH groups, so they tend to be very viscous. Right, here's a substance that's very viscous, so I just have this on the webcam here. I've been doing this every year, and I do not know if this is going to happen while we watch it. But there's this guy who is a chemist, and he made some sort of tar. And it became the world's most viscous substance. And I think in 2013, I forget the year, but it was viscous. It's so viscous. He started it in 1920. 1920s or so. And here we are in 2025, and only 9 drops have come out. Okay? 9 drops. So there's a website called the 10th Drop or the 10th Watch, and this was a chemist named Thomas Purnell who made it. And I think he was making some sort of tar for his sailboat. I don't know the whole story behind it, but this is a liquid, and it has a lot of viscosity. It's so viscous that from almost a century they put, they're waiting for the thing to just drop. And from this first synthesis till now, only 9 drops have come out. So there's a website in Australia that's looking for the 10th drop. Okay, this is a very fun, extreme or funny example of viscosity. So let's take a look and see if this viscosity or this viscous substance will drop. The 9th pick drop from the world's longest running lab experiment fell in April 2014. Now the watch for the 10th drop continues. Okay, it started in the 1920s, actually. So, and then I don't know when they started to put a webcam on there, but they started maybe like years ago. But and here is the webcam. So that's a very viscous substance. Okay.
You sure that's a liquid? It looks more like a solid.
It's a liquid. It's a liquid. So when it becomes at this level of viscosity, the lines between solids and liquids tend to be blurred. But I think it's definitely a liquid. A solid would have density. It would be hard. It would be rigid. It would definitely have a different arrangement or physical structure if it were solid. So we will just wait here till the 10th drop comes. All right, so this is an example of viscosity, and for the exam you just need to know viscosity is something that liquids have. Thomas Purnell, University of Queensland, I think it's in Australia. First professor of physics, radio experiment, 1927, to illustrate the everyday materials that can exhibit with quite surprising properties. Okay, here we go. C. Bailey, world's thickest known fluid, in other words liquid, and was once used for waterproofing boats. Wow.
Imagine they probably had to scrape it out.
100 billion times more viscous than water, and so on and so forth.
Yes, they must have like scrape it out of the container in order to use it.
Okay, it took 8 years for the first drop to fall, 40 years for another 5 to follow. Okay, so viscosity. I'm just reading this. Let me read this out. The late Professor John Mainstone became the experiment's second custodian in 1961. He looked after the experiment for 52 years, but like his predecessor, Professor Purnell, he passed away before seeing a drop fall. Man. That's rough. I feel sorry for the guy. All right, what people do for viscosity. All right, let's go back and review what are the 4 things that all liquids have. Go ahead.
Cohesion.
Surface tension. Yes. Okay, what's another one? Cohesion, adhesion, so they can attract to each other, or they can attract to the surface of the material, the glass. Cohesion, adhesion. And then what's the fourth property that all liquids have? Viscosity. Okay. So that 10th drop is very extreme. But usually with viscosity, what are we looking for here?
The resistance to flow.
Resistance to flow, but what functional group? What does viscous material have? Usually we look for OH groups. Okay, so on an exam, if you see a lot of OH groups decorating the molecule, you can guess with a lot of confidence that it's most probably viscous. So okay.
But are OH groups the only ones that have like only hydrogen bonding group that can be very viscous, or is it just usually OH?
It really depends on the structure of the molecule. We know that if the molecule has a lot of OH groups around it, it can generally have the tendency to be viscous. Yeah. If it has a lot of NH groups around it, then possibly. There's a substance in our body called hyaluronic acid, and those are generally viscous. And that hyaluronic acid, which is part of your extracellular matrix, they're also pretty viscous because they have NH groups and OH groups on the sugar. So yeah. But usually for the exam, lots of OH groups, more viscous, okay, because of the hydrogen bonding capabilities. All right, so these are the 4 properties of liquids that I'd like for you guys to know. Any liquid will have these 4. All right, let's go into a new topic now, and these are phase changes. All right, so this is going from, we'll talk about this one here. This is going from a liquid to a gas, and going from a liquid to a gas is called evaporation. Okay, going the opposite way. Okay, going the opposite way. Okay, this is a new topic now. Going the opposite way, going from a gas to a liquid. This is called condensation. Okay, you may have heard about evaporation and condensation. Okay. So with this phase change from liquid to a gas or gas to a liquid, I'd like to introduce the concept of vapor pressure. All right, vapor pressure. So first of all, this phase change, liquid to a gas or a gas to a liquid, is dynamic. Okay, so what do I mean by dynamic? It can go back and forth. Okay, it can go back and forth. Just as a liquid can go to a gas, that gas can go back into a liquid. And that liquid can go back to a gas. So we're talking about a dynamic situation that can go back and forth, back and forth. This is not static. Okay, it's free to go from one molecular state to another molecular state, freely, back and forth. Okay, so I'm just going to call it not just dynamic, but a dynamic equilibrium. Okay, this is a dynamic equilibrium. So with that in mind, let's talk a little bit about vapor pressure. First of all, vapor pressure is a pressure. Okay. Is a pressure. So when we say pressure, it means units of millimeters of mercury, atmospheres, okay, Pascal. Okay. Okay, so let's, on the exam or on the problem, make sure you get the units right. We should know what the units of pressure are from Chem 1. It's usually millimeters of mercury or atmosphere. Sometimes you'll see torr. Okay, it's not milliliters, it's not liters. Those are units of volume, right? Okay, it's not newtons, it's a unit of force. So pressure, okay, it's a pressure. And it's a pressure based upon this dynamic equilibrium of a liquid going to a gas. Now, when it's a gas form, okay, also known as vapor, that is when it can exert the pressure. Gases exert pressure. Gases will exert the pressure on the liquid. All right, so hear me out now. Just let's have this experiment together. Okay, so I'm going to draw two beakers. Okay, two beakers. Okay, one beaker is going to have water. Okay, two liquids. Okay. And the other beaker will have another liquid. We will call it propane. Okay, propane. Remember propane, its structure. Okay, so we'll call this propane, and we'll call this water. Okay. So imagine you have propane in one beaker, we have water in another beaker. All right, so remember this two liquids. Liquids are going to exert a vapor pressure. Now, what is this vapor pressure? And what is all of this about? Okay, remember this dynamic equilibrium I was talking to you guys before? Okay, so imagine you have a water molecule. Okay, a water molecule, and right now it's a liquid. Okay, it's a liquid, and let's say this water molecule evaporates. Okay, it evaporates, and then what will it become? A gas or a vapor. And what can a gas do? This is a dynamic equilibrium. Remember, it can go back and condense. Okay, as it condenses, it does what gases do and exert a pressure. Okay, so this dynamic equilibrium, we have on one side going this way, becoming a liquid, evaporation. This is dynamic. Okay, as it evaporates, it could also just as well condense. That's going down. And as it condenses, the gases exert a vapor pressure on the liquid. So we have evaporation here. As it condenses, it exerts a vapor pressure. It's a dynamic, back and forth, back and forth. So this is the situation that's occurring. It evaporates, condenses. As it condenses, it exerts a vapor pressure, because now here it's a vapor. As it comes back down, it's going to exert a pressure. Okay, it's the same situation with propane. Okay, it evaporates, and then as it condenses back down, it will exert a vapor pressure. So as it's going down, it condenses, it will exert a vapor pressure. Because that's what gases do, right? They exert a vapor pressure. All right, now the question to you guys here that I'm going to pose to you is, which do you think, a beaker of water or a beaker of propane, which do you think will exert the highest vapor pressure? Will it be the water or the propane? Okay, so this is a dynamic equilibrium. It evaporates and then it condenses. As it condenses, it will exert a vapor pressure. Okay, it evaporates. The molecule becomes a vapor or a gas. Gases exert a pressure. It will exert a pressure back down. It will exert a pressure back down on the surface. as it condenses. This is a dynamic equilibrium. But which one would have the highest, or which one would exert the highest vapor pressure? Okay. So what do you think the main intermolecular force is for water? Hydrogen bonding. That's correct, Jake. Which or what is the main intermolecular force for propane? Dispersion. With that being said, now, which do you think will exert the highest vapor pressure? One that's held together by hydrogen bonding, or one that's held together by dispersion? The one that's held together by dispersion will evaporate more. Why? The intermolecular forces are weak. We're not breaking bonds, but that's the correct. Okay. This is a weak intermolecular force. See, this propane molecule and this propane molecule are only held together by very weak dispersion forces. Okay. This water molecule and this water molecule have hydrogen bonding, which we already know is a very strong intermolecular force. So which is more likely to happen? Evaporation is more likely to happen here, or will evaporation more likely to happen here? To me, evaporation is more likely to happen here because it has a weak intermolecular force. Okay, and this is a dynamic equilibrium. As you evaporate, you condense. As you condense, you exert a vapor pressure. Okay? So just based on the fact that these are held together by very weak forces, they can evaporate, and as more evaporate, more can condense, because this is a dynamic equilibrium. Right? So this will have the higher vapor pressure. And this will have a lower vapor pressure, just comparing these two liquids. Right, so which one will have the higher delta H vaporization? What is delta H vaporization? Okay, it's the energy required to vaporize 1 mole of a liquid. 1 mole is the key word here. Which would have the higher delta H vape? The one held together by hydrogen bonding, or the one held together by dispersion? Energy. How much energy do you need to vaporize something? Will it be a lot if it's held together by hydrogen bonding? Okay, the answer is yes. So this would have, it'll take a lot more energy to vaporize 1 mole of water. Why? Why is that? Why does it take a lot of energy to vaporize water? Okay, what are you trying to break apart when you're trying to break apart the hydrogen bonding? Okay, so the energy that you have to put in, the input that you have to put in, the energy, okay, is going to be more to get this to vaporize, to get this to condense, or to get this to evaporate. So this is going to have a higher energy of vaporization. Which would have a lower delta H vaporization. Relative to this, this would be lower. Delta H vaporization. Okay, this is an energy. Okay, energy. Remember delta H in Chem 1? Okay, energy. Yes, go ahead, Kate.
Can you explain the vapor pressure again, like the relationship? Like, why would H2 have a low vapor pressure?
Because it's just harder to form a vapor, because each water molecules are held together by hydrogen bonding.
Oh, okay, so it's easier for the propane to form a vapor molecule.
Correct, because they're held together by dispersion. That's correct.
Okay, thank you.
And in that same vein, Caitlin, this will have a higher energy to vaporize because you're held together by the strong IMF of hydrogen bonding, so it's going to take a lot more energy. In joules per mole, or kilojoules per mole, it's going to take a lot more joules to vaporize this because it's going to break apart the hydrogen bonds. And here it's going to take less delta H vaporization, less energy in joules per mole because you're just disrupting the very weak dispersion forces. All right, so that's what we want to be keenly aware of. All right, I'm going to move on to the next page here. Let's go over this. First of all, just definitions here. Delta H vaporization is energy, okay, in kilojoules that is required to vaporize 1 mole of a liquid. So, I wrote in kilojoules, but you can see it in kilojoules per mole as the units, or joules per mole. So delta H vaporization. And here are some values. Okay, let's look at this. Water. Okay, boiling point is 100 degrees C. The delta H vaporization is 40.79. This is a number you do not have to memorize. Okay, but we call this the delta H vap, or delta H vaporization. So water has a very high delta H vaporization. I'm just looking at this. Ethanol is 78.3, 39.3 kilojoules per mole to vaporize ethanol. And this is also hydrogen bonding. Okay, diethyl ether. Okay, what did we say about ethers? Okay, they're polar, and you do not memorize these numbers. I'm just, they're just there as references. Okay, diethyl ether. Okay, methane. Okay, why do you think methane is so low? Okay, so low.
It's held together by dispersion.
Dispersion. Okay. Only need 9.2 kilojoules per mole. All right, so these are some of the numbers. You do not have to memorize any of those numbers, but it's just giving you some explanation of why we see these boiling points and why the delta H vaporizations are high for some, low for others. Okay. Water here is also hydrogen bonding. All right, so here we have delta H vaporization. Let's fill in this blank together here. So the more intermolecular forces you have, the more intermolecular forces you have, what will be the value of delta H vaporization, higher or lower? Higher. Okay, the stronger or more intermolecular forces, the more energy input, kilojoules per mole or joules per mole, that you have to put in to get it to vaporize, to break it from the liquid phase to the gaseous phase. Okay, so the higher the delta H VAP. All right, another thing I want you to know about vapor pressure, we're going to see this a lot. Okay, this is a common theme here in Chem 2. So the theme here is vapor pressure. Like so many things I'm going to teach you in this class, vapor pressure is quoted at a specific temperature. Okay. So change the temperature. What will you change? You change the vapor pressure. Okay, So it's quoted at a specific temperature. There's many things that I will teach you in this class that are temperature dependent, and vapor pressure is the first one that we're learning together that is temperature dependent. So we can have a graph here, the vapor pressure versus temperature graph, and it has this type of trajectory. Okay, this is the profile of something that has vapor pressure on the y-axis and temperature on the x-axis. Let me just draw that profile here. Vapor pressure on the y-axis, temperature on the x-axis. It's going to have this type of shape. Okay, if your vapor pressure is 1 atmosphere, and you take that 1 atmosphere connected to that point on the graph. Okay, this temperature here at 1 atmosphere is called the normal boiling point. Normal boiling point. Okay, normal boiling point. Here, normal means 1 atmosphere. So what does normal mean? 1 atmosphere of pressure. Okay, you take that 1 atmosphere, you connect it to the line, to the vapor pressure temperature graph, and you're going to get the boiling point. Okay, so for diethyl ether, that's this temperature. For water, that's this temperature. I think everyone knows it's 100 degrees C. And for this liquid mercury, it's this, 357 degrees C. All of these are normal boiling points. Why is it normal? Okay, because of 1 atmosphere. Okay? So you want to associate 1 atmosphere with normal. Okay, normal freezing point, normal boiling point, normal melting point, so on. Okay? So 1 atmosphere. Take it down to the x-axis of temperature, y-axis is vapor pressure. That's the normal boiling point. All right, so no, vapor pressure is quoted at a specific temperature. You change the temperature, you change the vapor pressure. And then 1 atmosphere is the normal boiling point. Okay, so these are the 3 important things. Okay, temperature dependence, normal is 1 atmosphere, and the normal boiling point is that where it boils at 1 atmosphere, that temperature. Those are the 3 important things I'd like for you to know. Okay. All right, let's go over a problem here that we'll see on the exam. I'll give you this on the test. I'll give you this equation. Okay, I'll give you the equation. You do not have to memorize it. Okay, I'll give you it. This is called the Clausius Clapeyron equation, and it relates vapor pressure to temperature. Okay, so let's say you have a vapor pressure at some temperature T1. Okay, vapor pressure at some temperature T1. And then we change that temperature to T2. Okay, we will get a new vapor pressure 2. Okay. All right, so this equation, if I give you 3 out of the 4, you should be able to solve for the other. Okay, so if I give you 3 out of these 4, you can solve for the other. And that's what this equation is about. Okay. So I'll give you, so this is one version of the equation. I kind of like this version. Okay, I kind of like this version, but this and this are the same. Okay, all I did was split this fraction into 1 over T2 minus 1 over T1. So you'll either get this or this on the exam. I'll give you one or the other. More than likely, I'll give you this. Okay? So let's go over this. Let me rewrite it again. I'll give you this on the test one more time. So do not memorize it. Okay, so remember our profile here. Vapor pressure on the y-axis, temperature T on the x-axis. What we're going to do is we're going to change the temperature from T1 to T2. And then we'll have a new vapor pressure. Okay, this equation, called the Clausius Clapeyron equation, bridges those together. So P1 is vapor pressure 1 at T1. P2 is vapor pressure 2 at T2. Delta H vap, or delta H vaporization. Okay, remember this, it's the energy required to vaporize 1 mole of a liquid. It's the energy required to vaporize, turn into a vapor, 1 mole of a liquid. And then finally we have R. Okay, so I will give you R also, it's a constant. And R here is 8.314 joules over mole Kelvin. 8.314 joules over mole Kelvin. Okay, I'll give you that too. So I'll give you this and this on the test. You do not have to memorize it. Do not. Okay, so let's do a problem. Okay, it's similar to your quiz, and it's similar to what will be on the exam. So we'll go over this, and we'll go over it again before the test. All right, are you guys ready? By the way, if you see the units here, what do you think our temperature should be? T stands for temperature. What unit should the temperature be in? Okay, they should be in Kelvin because the R is in Kelvin.
Are we going to have to...
Yes, you'll have to convert it. Okay, do we know how to convert this? Because we need to convert it because the R units are in Kelvin. Okay, the very units of this constant is in Kelvin, so we have to convert our temperatures to Kelvin. Okay, do you remember how do we convert to Kelvin?
273.15.
Right. Why do we have to convert to Kelvin? Because the constant in this equation has units that are in Kelvin. All right, so let's go over this. We'll see this similar one on the test. The vapor pressure of ethanol is 100 millimeters of mercury at 34.9 degrees C. What is the vapor pressure at 63.5 degrees C? So we have here VP1, we'll do it in green here. Vapor pressure 1 is 100 millimeters of mercury. Okay, what is vapor pressure 100 millimeters of mercury at what temperature? Okay, what is this in Kelvin? Did I bring my calculator? I hope I brought my calculator, otherwise I'm in trouble. So many calculators, but not one here. Do you have a calculator I could borrow? Oh, perfect, thank you. And it's not a full calculator, I appreciate it. All right, thank you. All right, 34.9 plus 273.15 is 308.05. Kelvin. So that's T1 at vapor pressure 100 millimeters of mercury. Okay, 63.5 degrees. $336.65. Kelvin. Okay, so that's T2 at vapor pressure P2, which we're trying to solve for. All right, so the first thing we want to do here, okay, step one in this problem is to convert all our temperatures to Kelvin. Okay, and as you stated correctly, we add 273.15. The next step here, you see the delta H vaporization. Okay, it's 39.3 kilojoules per mole. What do we see here? Joules per mole. So what do we need to do to get the units to cancel out? Okay, what do we need to do? We need to convert the kilojoules per mole to joules per mole, because what is R? R is in joules per mole. So we're going to convert delta H vaporization to joules per mole. Okay, how do we do that? We're going to take that 39.3 kilojoules per mole, and the conversion is 1 kilojoules is 1,000 joules. Okay, so you essentially multiply it by 1,000, and that will give us 39,300 joules per mole as our delta H vaporization. This is the energy required to vaporize 1 mole, convert it to a vapor, from the liquid to vapor, for ethanol. All right, and then the third step is to plug into equation. Okay, this is called the Clausius Clapeyron equation. All right, let's go ahead and do that now. All right, natural log of P1 here. P1 is 100 millimeters of mercury. Okay, here's another thing. I don't know how much math you guys are, but we don't put units inside the natural log. Okay, if you're a mathematical purist, you don't put inside a log any units. Inside the natural log, you don't put any units. So I'm just going to put the units after the fact. Get our answer, and then put the units. But don't put units inside the natural log. Divided by P2. Okay, this is going to equal to delta H vaporization. What did we make delta H vaporization? 39,300. Joules over mole. Okay, R. What is R? R is 8.314 joules over a mole Kelvin. This is our R here. Okay, what is 1 over T2? 1 over T2 is 336.65. You guys following along with me? Minus 1 over T1. What is T1? 308.05. Kelvin. All right, so to get our answer, we have to solve for P2. I plugged everything in. I plug in my P1 and my T1. I plugged in my P2, which is unknown, and at my T2. R is R, will always be given. And I converted my delta H vaporization to this, okay, joules per mole. So our goal now is to solve for P2. How will we solve for P2? This is how we'll solve for P2. All right, I'm going to do this on Antoinette's calculator. Okay, everybody's calculator is different, but I'll just go ahead and do it. I'm going to do this in one fell swoop. Okay, one fell swoop. And those of you, maybe Jacob, you can double check my calculations. So this Kelvin and joules per mole cancels out with that joules per mole. Okay. This Kelvin cancels out with that Kelvin. Joules per mole cancels out with joules per mole. Do you have a complicated calculator, Antoinette? Okay, 1 divided by 336.65. Okay, minus, okay, I'm going to do this in parentheses, minus 1 divided by 308.05, close parentheses. Okay, this minus this is that number. Okay, this minus this is that number. Make sure you put this fractions in parentheses. Okay, this minus this fraction minus this fraction is this. Negative number times 39,300 times 39,300 is that divided by 8.314. Okay, divided by 8.314. And I am getting negative 1.3036. Anybody else get that? I see a yes. Okay, all I need is one yes and I'm good. So thank you. All right, natural log of 100 over P2. Negative 1.3036. I'll just add some digits here. All right, now we have a problem here. The problem is we need to solve for P2, but how will we solve for P2, vapor pressure P2, when it's stuck inside the natural log? Okay, this is how we solve for P2. You see that natural log in brackets? Okay. What we will do is we will take the inverse natural log of both sides. See, whatever you do on the left-hand side equation, you got to do on the right-hand side equation. So we're going to take the inverse natural log of both sides. Okay, anybody in math know what the inverse natural log is? I used to advise. I had an advisee, and she was a math major and a chemistry major and something. So she was taking all these maths, discrete math, logic math, linear algebra. I was like, oh my gosh, she's smarter than me when it comes to math, maybe even chemistry too. So to get the natural log out, you're going to take the inverse natural log, and the inverse natural log is called e. Okay, e to the power of x. Okay, so we're going to take e to the power of natural log over 100. E to the power of natural log over 100 divided by P2 equals e to the power of minus 1.303613. Okay, I added some extra digits there. Okay. Okay. What's e to the power of natural log of 100 over P2? Remember, they're inverses of each other. So this is the way you pop out this number. E to the power of natural log of 100 over P2 is just 100 over P2. They're inverses of each other.
So then essentially like the e to the negative 1.3 and all those digits basically equal 100 over p2. Is that what you're saying?
Yeah, so inverse e, no. Inverse log, where's your e button on your calculator? It's usually the inverse natural log. Inverse natural log. Okay, that's natural log, good. I want the inverse of that, which is e.
It should be the same button, you just have to hit
The second button.
Yeah, there we go, e. Okay. So this calculator's a little bit different. On mine, they're usually like, the second to natural log. Okay, so here on this particular calculator, every calculator is different. Okay. Here's the natural log, and then you're going to go e. Okay, e. Okay. So you don't have to do second here on this calculator. On mine, you got to do second. On yours, you have to. On yours too. Okay. E to the power of negative 1.303613. 0.2715. I'll add some extra digits here. Okay. And let's quickly solve for this here. Solving for P2. It's going to be 100 divided by 0.27155. I just added some more S significant figures, but we'll cut it and when we report our final answer. So what's 100 divided by 0.27155? 368. We'll just do three sig figs here. Okay, three significant figures. 368. What are the units? Okay, don't forget to add back the units. Yes. Okay, add back the units. Okay, otherwise on the exam, I'll take off half a point. Okay. So this is the answer. All right. Okay, can we do this on the exam, particularly this part? Can we? We have that confidence?
Maybe like practice it a bit myself and then I'll probably be able to.
We'll practice a couple more before the test. I think there's a practice one on the quiz. I think there's one on the homeworks as well. So at 34.9 degrees C, the vapor pressure of ethanol is 100 millimeters of mercury. Okay, in this problem, they raised that temperature from 34.9 to 63.5 degrees C, and the vapor pressure increased to 368 millimeters of mercury. Okay, so if you raise the temperature, what happens to your vapor pressure? It also increases. Why do you think that happens? What happens when you raise the temperature of something? Okay, and as it starts to boil, okay, what do you think is going to happen as it starts to boil? More vapor, more gas, which means more condensation, which means more vapor pressure. That's correct. Very good. All right, let's just review quickly here. All right, so a question like this on the exam. So make sure you're comfortable doing this. I notice students have issues with this area here, so you can see me in my office hours or watch some videos that I posted on Canvas related to this. All right, the last 2 minutes, let's just review here. This is just review. All right, so let's say we have let's say have water, ethanol, and propane. Okay. Which one would have the highest vapor pressure? Actually, we'll just do water in this. Here. Okay, without looking at any textbook, without looking at our phones, which would you think would have the highest vapor pressure?
What's the one? The bottom?
Propane. Okay, so this would have the higher vapor pressure. Okay, what about delta H vaporization? To vaporize 1 mole, that would be high, this would be low. Okay, and then the boiling point, which would be higher and which would be lower. Okay, we know that's at around 100 degrees C, and this would be low. Okay, and what would be the IMF for this? Hydrogen bonding, which is a strong attraction, and what would it be for this? Van der Waals, or what we're learning as dispersion, which is weak.
So, wait, why does water have like a lower VP? Because I thought there was like there was like an OH there.
Vapor pressure.
Oh.
It's hard to form a vapor because you have to boil it to get it to form a vapor to disrupt the hydrogen bonds.
So with vapor pressure, it's basically about how much you use it to like break up the bonds, essentially. Okay.
To disrupt the bonds, yeah. It's harder to make this a vapor than propane.
Okay.
Okay, so vapor pressure, delta H vaporization, boiling point, and the IMFs, these are all correlated to one another. All right, I will see you all on Thursday. No lab today. All right, thanks.